Hey, everybody. I am particularly pleased with myself to be bringing you this video, number 6 in our series, and I'm going to tell you why. So, I'm making this video in early 2025, and a few weeks ago, maybe a month, Sky got his first peer review report. So, this is where, well, I guess an anonymous mathematician somewhere looks at a paper submitted for publication and writes up his reaction and his opinion about it, any issues that he finds, and then the author of the paper receives that write-up and has a chance to edit the paper, fix it up in response to whatever comments. So this happened, and Sky and I were looking over the report and talking about different parts on it and so on. And we realized that one of the really important parts of the paper needed him to establish a certain fact about W of n, about the density, in order to make it more clear that the approach he was using was going to work out. And out of that conversation ultimately arose the proof that I'm going to show you in today's video, which establishes Hughes's corollary. That's right. I helped out, and Sky was extremely gracious to put my name on this little slice of the paper. I even got a footnote at the bottom of the page explaining to the reader what a great friendship me and Sky have. As far as for publication mathematics papers typically go, this is as sweet as it gets. So thank you, Sky. All right, let's get into it. This is video 6, part 2 of our 3-part series on the topic of density in all its forms. I mentioned last time that once you have proven the basic density, you can conclude that any arbitrary interval will actually contain an infinite number of points. But now we're going to look at a result that you might say is even stronger than that. As I mentioned, this result will provide some important supporting evidence for a step that appears later on in the paper. Compared to the last video, we are switching gears here in one important way you need to keep in mind. Instead of talking about the full image of Wn for all integers that exist, we're now working in a world where the integers are limited to some maximum value, capital N. So we want to draw this conclusion about how W of n behaves while it's still on its way to infinity, but not there yet. Now, it doesn't really matter how big capital N needs to be to make it work. We get to make big N whatever we want it to be, but it has to be finite. We can't be appealing to actual infinity in the way that we make our argument. Okay. So anyway, we'd like to show for any arbitrary interval on the unit circle that as capital N grows beyond some minimum value, that we can eventually find a number of points in the interval that is greater than the expression n to the x, where x is a number less than 1. Now, I say eventually. Obviously, this is not going to be true for small n's, like 100 or something. But we want to show that if you give me an arbitrary interval and you give me a value of x less than 1, even if it's 0.999 or something, then I can deliver to you a number for n that is big enough that you'll find n to the x points in your interval, and then that remains true for all higher values of n. So that's the challenge. Then, as a bonus, at the end, we're going to prove that we can do this even without knowing the location of the interval, as long as we are told its size. All right, so here's how we do it. So we're given, as I said, an arbitrary little arc on the circle. Step one, we find the mirror image of that interval on the other side of the circle. Step two, we locate a point that is in there, and we call the integer that maps there n naught, or n sub 0. Now we know we can do that because of our proof that W is dense from the last video. And we haven't actually stated what capital N is yet. That comes later, right? Right now, we'll just temporarily set capital N at some number high enough to allow n naught to appear. Then let's flip that point back to its own mirror image, which is actually in the interval that we were given. Now, this point is not the image of some integer under the function w, right? It's just a reference point. Technically, it's negative w of n naught, right? Now, if we multiply n naught by one prime number, if that prime number is big enough, then we will get a point from w in our target interval. There's a little space in there, right, beyond negative w of n naught, where we could fit it in. And if we multiply by just one prime number, we know that changes which side of the circle we're on, right? Because odds become evens and evens become odds. And we know that primes become arbitrarily large, so that their contributions to the angle become arbitrarily small, small enough that we don't leave the interval when we do that. And you should see now, this is why we started on the opposite side of the circle, so that when we multiply by one prime, then we end up, where we want to be. In fact, if you reflect on it for a moment, you'll find that there is some prime number, call it p sub j, large enough that itself and all larger primes each have this property. They each create a small enough increment in the argument that we stay within our little interval. So now let's consider all of them as a group. We're not going to multiply by all of them at the same time, right? We're doing each separately. So the points in the interval are w of n naught times p sub j, w of n naught times p sub j plus 1, p sub j plus 2, blah, 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 and so on. And that goes on until we decide to stop. And we'll stop with some largest prime that we'll just call capital P. At which point, let's say we've used m consecutive primes. So we've added m points to the interior of our interval. Now we can pick any stopping point, which allows us to put any number of points into the interval. And we know how large capital N has to be to get us there, right? So let's specify that. As long as capital N is greater than or equal to n naught times capital P, then the interval will contain however many points we've decided to add. And of course, when n gets that large, the interval might contain a lot more points by coincidence, but it contains at least as many as we have deliberately added, right? So now the question becomes, can we add points in this way fast enough so that the number of points in the interval m can be shown to ultimately be reliably greater than n to the x, where x is any number less than 1? Well, you may find that intimidating, because what if x is 0.999? I mean, to me, n to the 0.999 looks like a number that is almost as big as n, right? But actually it's not. For really large n, if you ask, approximately what percent of n is n to the 0.999? The answer is 0, actually. Well, when n is super phenomenally large, then it rounds to 0% in spite of how it looks. I was thinking of demonstrating this for you in Excel, but Excel declined to perform the calculation. So if you're wondering how big does n need to be for this to be true, it's bigger than Excel can handle, apparently. But the mathematical principle here is clear. It does happen. So, yeah, math is weird sometimes. Anyway, we now want to compare the number of points we added to our interval, which we call m, to the value n to the x. We want this ratio to be greater than 1. So how can we address that? Well, we have this thing called the prime number theorem, okay, which is approximating the density of prime numbers. The number of prime numbers less than some value k is known to be around k over log k. So that's a statement about the total number of primes up to some limiting value. But we are using a series of primes that doesn't start with the first prime number, right? It starts with some random prime that we called p sub j, so like the jth prime. But we can still use this. Let's just start plugging the values in and see where it goes. The total number of all primes up to p should be equal to j minus 1 plus m. If you recall, we did use p sub j. So that means p sub j minus 1 is the last one that we did not use, right? So we're going to have first j minus 1 primes. Those are the ones we don't use, plus the ones we do use, and we call that capital M. So you add those together, and that's the total number of primes in a series up to big P. And that will be approximated by k log k, where k is how high the primes can be. But what would that value be in this case? Well, we're calling our biggest prime capital P. So k in this case is capital P. So we can relate that to P over log P. Now, since we're interested in M, we can move the j minus 1 to the right. And then M is approximated by P over log P minus j plus 1. So we'll put that in the numerator of our ratio for M. Now, what about n to the x? I think we stated before that our value of capital N needs to be as big as n naught times capital P. We can just raise that to the x power to get n to the x, and then distribute the exponent x. I don't see anything else we can do at this point, so let's just put that into the denominator for our ratio, and we'll see if anything good happens. Well, okay, I see one piece of algebra that we can do now, and that's to combine the powers of p, right? So let's rewrite this with p to the 1 minus x power in the numerator. So now we've transformed our ratio that we want to be greater than 1. What kind of conclusions can we draw about this? Well, here's the thing. Some of these variables in here are fixed, and some of them can rise in value if we want them to. N naught is fixed, right? That's just that one point that we found in the mirror image of our interval. X is fixed. That was given to us. J is fixed. That's the index of the lowest prime in our sequence. But then there's P. And we could just let P run, man. Like, P can be as big as we want it to be. As it grows, the N and the X and the J, they're going to start looking pretty small after a while, right? Eventually, they're not going to matter when it comes to evaluating what this ratio is doing. So ultimately, we're just comparing P to the 1 minus X to the natural log of p. So what can we say about this? 1 minus x is a positive number, since we started by saying x is less than 1, right? And log is an increasing function, so both of these are growing as p grows. Now, I'm tempted to wave my hands in the air and say, we're done, and we got the result we wanted. This is one of those situations that you run into pretty often in like college level mathematics, where you have two expressions and you need to know which one is ultimately growing faster. It won't matter where they start out. It just matters how fast they grow. If one of them is growing faster than the other, even if it starts out lower, it will end up being greater. It just takes time. And anybody with a little experience in this area will just, remember that p to a positive power grows faster than log p. But let me make the case a little bit more detail, since this is an educational video. The way mathematicians reason about a situation like this is they're looking at the derivatives to see how fast the functions are growing. Like which derivative ends up bigger eventually. The derivative of p to the 1 minus x is 1 minus x, p to the negative x, right? And the derivative of log of p is 1 over p, or p to the negative 1. In the beginning, that 1 minus x multiplier might be significant, but it's fixed. And eventually the value of p grows bigger. As the value of p grows bigger, that slightly more negative exponent at the bottom on p to the minus 1 is going to result in a lower derivative for log of p. And if log of p from that point forward is, growing, but growing more slowly than the numerator forever, eventually the numerator is going to be bigger and it will keep getting bigger forever. So that ratio will actually be unbounded. Or as Sky says in his paper, we can choose m large enough so that this ratio exceeds any positive number. So the ratio m over n to the x will eventually rise and keep rising, definitively placing more points in our interval than our benchmark n to the x. Neat, huh? Now, we have something else we wanted to prove. Do you remember? In the first proof, we're given an interval and a value for x, and we have to provide capital N. Well, we didn't provide the N so much as we demonstrated why the N has to be out there somewhere, out in the Badlands, where maybe there aren't enough atoms in the universe to represent the value of N. But that's okay. We're not inviting N to dinner here. It can stay out there where it is. We just need to know that it's there somewhere. But as I was saying, in the first proof, we're given the interval and the value of x. This time, we are given only the size of the interval and the value of x. Now we need to prove that there will exist a single value of n big enough that beyond n, it is simultaneously true that every possible interval of a given size contains at least n to the x points. Now, the nice thing is we can climb onto the scaffolding that we already built in order to put this together. We already know that each interval of this size will have some value of n that works for it. Like, just for the sake of argument, what if there were just two intervals and we wanted to prove this? Well, we know each interval would itself have a value of n beyond which there are enough points in that interval. And we can call them, n0 and n1. We already proved that. Then we just need to take whichever one of those is bigger. And that would be the n beyond which both intervals contain at least n to the x points. So that's nice and easy. And you can use that method as long as the number of intervals you want to cover is finite. But if they're infinite, then it's not going to be quite that easy. Like, imagine that you had an infinite number of intervals, and the first one has an n of 500. And the next one has an n of 501, and the next one has an n of 502. and so on. Well, if that were the case, it could be true at the same time that, first of all, each interval does have a value of n beyond which it eventually contains n to the x points. But also, it's true that there does not exist any value of n beyond which we can say that all the intervals contain n to the x points. Infinity is just hard sometimes. But luckily, that's not what happens in this case for W of n. We are going to prove what we want to prove. And here's how we're going to get around that little difficulty. If our interval has a total width, let's say, of epsilon, I'm going to make a smaller number, maybe z, that's equal to epsilon over 2. And then I'm going to take 1 over z, which is probably a pretty big number, and I'm going to round that up to the next whole number, capital Z, okay? So capital Z is generally going to be slightly bigger than 1 over Z. Sometimes it'll be equal. Who cares? So let's zoom in on our circle. And I will zoom in so far that it looks perfectly flat because I don't have a big graphics budget, and that's an easier picture for me to create. Now, even though capital Z is quite large, it is finite. Okay? I'm going to divide the unit circle up into Z, capital Z, adjacent sections. And each of these adjacent intervals have a width that's less than or equal to little z. So at most, they are half the size of epsilon. And then I'm just going to apply the method in our proof to get a separate value of n for each one of these finitely many intervals. We know that works. So I'll have like n1, n2, n3, n4, all the way to n sub capital Z. Just pretend that you see the subscripts. And then I'm going to take the maximum of all of these n's, which I can do because there's only a finite number of them. Now, I claim that this max n value works for every possible epsilon-sized interval. Why? Because no matter where you put it, every epsilon-sized interval must fully include at least one of the z-sized intervals, which are half as big or smaller. And gosh, if there's n to the x points in the smaller interval, then the bigger one must have at least that many points. And so we have shown that our result holds for all epsilon-sized intervals at the same time. As we let n run, we will eventually come to a point where even though n is still finite, we will get more than n to the x points, not just in one arbitrary epsilon-sized interval, but in every epsilon-sized interval. And that is what's known in certain places as Hughes's corollary. Stay tuned for the third and final installment of our density journey in video number 7.